All right. So today is Tuesday the 24th. And so there's a tutorial due this weekend. It is on templates, which we're going to take today, which aren't that difficult, but we're going to go over all the nuances and things in there. Um, I will release tutorial 6 sometime this week, and then in about 2 weeks, assignment 4 is due. Assignment 4, also you need templates for it and files, which we should finish all of that this week. So then you'll have all of next week to work on it if you like. Yeah, I think that's about where we stand. The final exam, the coding portion is going to be based heavily on assignment 4, similar to your tests, right? How they're kind of stripped down versions of the assignments. So yeah, you should, try to get familiar with the architecture and how it all works together and things like that. So any questions? Okay. So today we're going to start with a woo clap, and then we will move on to templates. The woo clap is on operator overloading, which is all of basically what we took last week. So, oh, am I in the wrong one? There we go. Am I the wrong one again? Did I do the wrong one last time? Yeah, good enough. We'll do this one. I get confused because it's your sections A, B, and C, but the order that I see you guys during the week is B, C, A. So then sometimes I'm like, oh, the first one's A and whatever. So I'm occasionally mess up which section I'm supposed to be using, but okay, lots of participants today. Yeah, I think this is the this may be combined with the other section, but that's fine. It won't. Oh yeah, look at that. It should not affect the should not affect the results. When should an object return by a function from a function by a value, right? So when we talked about operator overloading, there was a lot of emphasis on sort of what the arguments should be and how they should appear, and also return values, right? So we should think, we want to enable chaining whenever possible. So often we want to return something, but sometimes we want to return by value and sometimes by reference. So what is the for returning by value, what is sort of the common theme, I guess? One thing we might say is that when it's returned from a const function, I mean, it's not a bad guess, right? Because if it's a const function and we return something, that something cannot be something that we can modify, right? Unless it's a temporary variable. But if I return this, right, then I'm not allowed to modify that. So if I return by reference, returning by value is a safe bet, or should be. But if I return by reference, then I have to make it a const reference, okay? So here I don't necessarily have to return by value. When returning this, well, certainly not. Usually this would be returned by reference, right? Really the common theme is number 3, when it's a temporary object that I allocated in that function. If I return it by reference, then what happens is, well, as soon as I return from that function, it gets popped off the function call stack, and now that reference is now stale, right? It's referring to some piece of memory that I might not even own at this point. So the compiler will give you a warning about that, but it'll still let you do it. So yeah, the answer is number 3. And you guys combined with last class, that's mostly what you got. Which of these operators for the time class should return a time object by reference? That is the return type is time ampersand. Okay, so kind of the rule is in general you should return by reference, whenever possible, unless you are certain you should return by value, but there are. Now it's, I guess, so we said return by value is when I return a temporary object. Now, which of these would return a temporary object is, I guess, the relevant question. So this here, the operator plus equals, well, I should return something. I should be able to embed that in another expression. So it needs a return value that it can use. And usually you return whatever the left-hand side operand is, and you would return it by reference. Because maybe I want to add more things to that same variable. So this would be returned by reference. The plus operator, well, here I want to add two things, the time object and, well, we can presume another time object, but really anything here. But the left-hand side operand and the right-hand side operand should not be modified, which means I want to combine them and sum them up, but that should be in a separate variable. Right, so I want to make a temporary object for plus and return that. So number 2 should return by value. So number 2 would not return by reference. This is kind of a trick question. So the question is, which of these returns a time object by reference? This, of course, does not return a time object at all. The O-stream operator should return an O-stream object. So not number 3. Number 4, the assignment operator. Again, I want to enable chaining, and to do that correctly, probably I want to return the variable itself. So this would return a time object by reference. Finally, the plus operator, and we're passing in a parameter, an int. Okay, so that's a dummy parameter, and that means this is the postfix operator, right? It's I plus plus, not plus plus I. And so in the postfix operator, we want to increment the value of the thing, but we want to return the previous value, right? So we want to save the value, first of all, in a temporary object. We want to increment this value and then return the temporary object. So this would be returned by a value. So the 2 correct answers are 1 and 4. Questions? Okay. Oh my goodness, giving it away. All right, here I have 3 overloaded definitions for the double equals operator. Just the, not the implementations, but just the declarations. And so one of them gets called in this line here. And so which one would that be? So yeah, let's consider what these all mean. So this is, of course, going to be a global function, not a member function. That means both operands are given explicitly. The left-hand side operand is an int, and the right-hand side operand is a time object. Down here, the left-hand side operand is a time object, and the right-hand side operand is an int. So it would not be this one. Now we come to the member functions, where the left-hand side operand is implicit. It's the this pointer, and this is a time object. So the time object appears on the left, so it's definitely one of these. On the right, we have an int, and the right-hand side operand is given as an argument, so it would be number 2. Yeah, so most of you got number 2, most of the last class as well. Finally, I think finally actually, but one of these would be a global function, so which one? Or which ones? I guess probably these are select all that apply. And so we have to think about what does it mean? What is the difference between a global function and a member function? Well, I mean, there's an easy way, sort of, it works pretty well, is that you can consider global functions have to explicitly list every operand, right? So that if it's a binary operator, such as this, that has a left-hand side operand and a right-hand side operand, then both of those are explicitly listed as here, right? So this would be a global function. The double equals operator, also a binary operator. And again, we have two arguments. So this function signature is of a global function. Here we have the less than operator. That is also a binary operator, but we only have one argument, right? So the left-hand side operand is implicit. It's the this. So not number 3. So number 1, number 2. The plus plus operator. That's a little bit tricky here because we do have a parameter, but it is not anything we're interested in. It's not a time object, right? So we're returning a time object. This is the dummy parameter that tells the compiler that this is the postfix operator. So technically, we are not giving any operands as arguments, which means that the operand is given implicitly as the this operator. So this would be a member function. And finally down here, well, we have the opposite. There's no dummy parameter, but there is a parameter of a time object. So it is a unary operator in that one operand is given explicitly, so that's a global function. And so if we look, yes, 1, 2, and 5 are all global functions. All right, questions? Okay. So yeah, that's about it. I guess you and the other class are combined with this, but it's actually easier that way. I didn't know I could do that. All right. So we will move on now to... Oh, here I had two web pages open. All right. We will move on now to templates. So templates are cool. They're really interesting. It's your compiler using pattern matching to sort of make magic stuff for you. And although we're taking very simple versions of templates, you can do some amazing, clever things with them. Now, it's not always a good idea to do clever things because they can be confusing and error prone, but they are kind of cool. So we're going to give an overview of templates and why do we care. And then we'll talk about function templates specifically, and then class templates. You'll see that, and we're going to explain what the compiler does when it makes a template. And then I think, are we taking the STL vector class? I may have moved that into the, so this will come later, maybe next week. All right, so some of the principles of object-oriented design is abstraction, data abstraction, and otherwise. We want to separate abstract interfaces from concrete implementations, and we want to reuse code whenever possible. We want if we write a piece of code, if we can make it applicable to a larger context, then often that's a good idea. Not always, but. Mechanisms for code reuse, use existing libraries. All right, so I'm gonna put an asterisk there because you should take that with a grain of salt. An outside library is not always the best solution. Some of them are poorly maintained or not maintained, right? There's a whole, like the internet is a graveyard of abandoned libraries. But things like the STL you can usually count on, right? They've been maintained for, probably decades at this point. And they're not going to be stopped maintained anytime soon, right? So, and also using existing libraries everywhere. There are languages that are terrible for this, right? And in terrible, I mean that sometimes they're very convenient, and then other times you get into this like dependency hell where your libraries don't work. This version does not work with this version, and blah, blah, blah. And so you're debugging basically, instead of debugging code and logic, you're debugging like package management, which I particularly hate. But so libraries can be very useful. Just be careful. The other way we can reuse code is template programming or generic programming. So this usually is for sort of very specific cases, often to do with collection classes. Right, I want to write a general algorithm. When I write a collection class, I don't really care about the data. It's not, I don't care what I'm storing. I'm just storing a bunch of stuff, and maybe I need to sort or find or do all those other things. So I want to write general algorithms that'll work for any data type, basically. So in C++, to do that, we use templates. This is almost precisely like generics in Java. But of course, you know, C++ came first, so the templates came first, and the templates are really sort of a very, very simple version. Java took basically all of C++'s ideas and then tried to like get rid of the dangerous stuff. So I think they did a pretty good job, but in C++, we go back to the basics. So our goal basically is we want to write an algorithm that can take different data types. And we want to write it once and then reuse it a bunch of times. And so the approach to this is we're going to pass in the data type as a parameter to our template, and then it will build a function or a class based off that. All right, so to start with, we'll talk about function templates, and then we'll go to class templates. So in particular here, we're going to look at global functions. All right, so let's just jump into that. So here in this piece of code, we have this, well, we have a function declaration here of max, and it takes 3 ints and returns an int. And if we look down at the implementation, well, the implementation is quite simple. We have 3 things, and we want to see which one is the biggest. So we just remember max value, remembers the biggest thing it's seen so far. The first thing it sees is v1, so that is the biggest thing we've seen so far. And then it says, well, is v2 bigger than the biggest thing we've seen so far? And if so, we're gonna change it to v2. And then we say, is v3 bigger than everything we've seen so far? And if so, we change it to v3, and then we return it. Okay, so very simple logic. And when we run this, well, you can imagine what it's going to return. v1, so the max int is 44. And if we look, the max int is indeed 44. So that works great. Okay. Well, maybe we want to do the same thing for floats, right? That seems reasonable. Floats basically operate on the same logic. However, they are a different data type. I can't pass a float in. It'll do an implicit conversion, and I'll lose information. So I probably want an entirely new function. And to do that, well, I have the pattern that works. So I'm just going to copy and paste that. I'm going to replace all of these with float. Right, and there's my declaration, and then for my implementation, well, floats and ints have this assignment operator and this greater than operator in common. And so all I need to change is, again, all instances of int to float. And then all the logic stays the same. And then when I run this, I get the maximum float is 44.5. Right, so again, I just did the most straightforward thing possible. I copied and pasted it. I did a find replace int for float, and it works perfectly. So then maybe I want to do chars. All right, so a char is basically an int, right? It's just an int, and there's an associated table. So I give you an integer value with 8 bits, and you tell me which character it corresponds to, essentially. But being an int, it means I could do math on it, and I could do comparisons. In particular, I can use the greater than operator. So I can do the same thing again. But this is getting kind of tedious, right? And also, I'm a human being. I'm prone to making errors. So what we want to do is we want to outsource this copy, paste, find, replace to the computer, which can do it correctly basically every single time. And so how I do that is I make this into a template. And I use t as sort of a placeholder value. And then I don't need this anymore. And down here, I'm going to do the same thing. I'm going to replace all instances of int with t. And then I'm going to get rid of this. Okay. I need a template. All right, so this declaration, I was asked, and it's a valid question, like when does this end? So what is template being applied to? Am I allowed to put spaces here? Yes, I mean, it's sort of implicitly going to be applied to the next logical thing here, whether it's this case, it's a function declaration. Down here, it's an entire function. Basically, so ignoring white space, it looks for the next thing it can be applied to. Maybe it's a class. When I run this, I still get the max int is 44, the max float is 44.5, and the max char is Z. It looks like the capitals come before the lowercase in the ASCII table. That's all. So yeah, all of these appear to work great, and all that happened was when we called this, the compiler looked for a matching function. It couldn't find it. But lo and behold, it found this, and this matches the pattern, right? So I have 3 of the same arguments of a function called max, and that's what I have here. So the compiler does this. It does a copy and paste of this. It does a find replace t with int. So now I have a declaration for this function. And then down here, it does the same thing. It sees this is a template, and it needs it. It does a copy paste, find replace, t with int, right? Exactly like we would have done, but it's much better at it. And then now it has another function and it compiles it. And if it compiles, then you're good to go. And then it comes down when I call the float version, it does the same thing. It looks for a matching function, doesn't find it, but finds this pattern, copy, paste, find, replace. And it does the same thing for char. And the only thing that it requires, all of these work on the same logic. They all have the assignment operator and the greater than operator in common. So if I do a copy, paste, find, replace, and try to compile it, it compiles. And that's all that happens. Right? So now I made 3 separate functions based on this one function template. Can you make different templates for different types in the same function signature? Sorry, I don't quite understand. If you can give me an example. As in maybe one template. If I wanted to do that, I would have to do something like this. I would have to specify that there are 2 different types. Oops. And then I could say, what'd you say? Add t, v. And then I could substitute t and v with int and float. That brings up an interesting question, though. So hopefully that answers your question. I do want to try something. What happens if I do this? That might still compile this. Even though I gave 3 of the same thing. No, it does not like that at all. I was thinking I'd get away with it. So if I use 2 different type declarations, it looks like I need to do 2 different types. But yeah, I can explicitly say that, well, the first one is of this type and the second is of this type, and then we can later on define what those types are. Yeah, we're getting to that. So I said he mentioned we have class up here and type name down here. That is correct. And what is the difference in this context? Nothing. For whatever reason, You can use either of these, and there is, as far as my research has found, and I did 10 minutes of searching, so there might be an edge case that I missed, but there's no difference. If I use class or type name, we're going to see later that type name has another use. But for the template declarations, both of those work equally well. I tend to use class because it's shorter, right? Type name is just more to type. So yeah, the other thing is that I used T up here. The woo clap? Oh, you just missed it. It was the very first thing we did. There'll be another one at the beginning of next class, most likely. Down here, up here, we used T. Down here, well, we didn't have to use T. What do I do? Right, I can say S. And then I can still compile and run it. So this does not have to match the function declaration. These are just placeholders, right? It's going to do a find replace, and after the find replace, that's what matters. Does the logic still work? Yeah, sorry, man. All right. So yeah, those are a couple of things. Any questions so far? Okay. Well, let's test out this template. So I'm going to make a bunch of time variables, and then I'm going to call max on time and see what happens. Right? What do we think is going to happen? Oof. Well, obviously the compiler is not happy, but specifically, why is the compiler not happy? Well, we can look. This is one of the problem areas, right? There's V3, and then I'm sure there's V2 up here somewhere. Well, as usual, when it comes to operators like C++, oh, there's V2. Really does a lot of digging. The compiler does a lot of digging to make sure that there's nothing it missed here. So basically, when it did the copy, paste, find, replace for here, replacing T with time, that worked no problem, right? This is just a declaration. When it tried to compile this, it got to this comparison operator. Now, a time class has an assignment, but the comparison, the greater than, it does not currently. So this failed, right? So it just didn't compile. Exactly as if we had tried to write this with, and did it ourselves, right? Copied and pasted and put time in there. It would not compile either unless we had this greater than operator overloaded. How would you choose the function's return type? Yeah, well, you would know which one it was, right? So you would have, it can return any type. It doesn't have to return like the generic type. So out of, you would choose if it should return a type that matches the first parameter or the second parameter. That's just a choice that you would make based on what your function does. So it's not always going to be, it really depends on the context. All right, so the problem is we have a type that does not match this pattern, right? I don't have a greater than operator, but, well, we know how to overload operators, so I could just add one. And I'm going to be a little bit lazy. I'm going to write it in the header. And I'm just going to use the convert to seconds function to do this. So I'm going to return convert to seconds. It's greater than t dot convert to seconds. And then logically, that should give us what we want. So now when I try to compile and it substitutes time for s, well, look at that, it compiles. And when we ask which is the greatest time object, it says 1654. And that does appear to be correct. Okay, so So using templates in conjunction with like operator overloading gives you a powerful way to define algorithms, and then I can use them on whatever data types I like, right? If I just choose to implement the correct operators in my data type, then I can run those algorithms. And the compiler is doing all the work. And, it is important to note, I made 4 different calls to this max function with 4 different types. That means 4 different functions were made. They are not all the same function, and if I don't, it doesn't make, it doesn't use every single type it can find. It only looks for the called functions. All right, questions? Okay. So what happens if we do, well, we can overload these functions with non-templated versions, right? So here I've declared a max function that fits this pattern. And of course, I do make a call to this function. And so down here, let's say that I wanted to write, or I had maybe a pre-existing version of this. Non-templated version. Right, so the compiler is going to look, and if it sees that we have a non-templated version, then it's going to use that. But here, when it goes looking for a matching function, of course, it only finds the templated version. So if we run this now, when we call for max int, it calls the non-templated version, right, and ignores the function template. So we can overload functions with non-templated types. Right, the stack or the heap or the special memory place. So the functions actually, they go into the code segment, right? Because this can all be determined at compile time. None of this is done at runtime. So at compile time, the compiler knows that it needs 4 versions of this function. And so it makes space in the code segment, right? So at the end of the day, if you think of it as the compiler does a pass where it looks up all of these and then builds those functions, and then it does a second pass where it tries to compile it, well, then this is no different than if we wrote all these functions ourselves, right? Which we could do, and which we started out doing. The compiler does the exact same thing. So those are just functions. They go in the code segment, the same as any other function. I cannot add new functions at runtime. Compile time is when they're all determined. So yeah, that's a good question. I like where your head's at. You're thinking about memory and things like that. Other questions? Okay. And I think that was all we needed to show. And in terms of overloading also, I could do, well, you can overload, this is technically an overloaded version as well, and you're definitely allowed to do that. Okay, so yeah. That's all stuff we took. So what happens is we write a function with a generic type marker, t in this case, as the type of certain variables or parameters or whatever. And then when we call the function, it uses that when it tries to build the actual typed version of this. Right? So the compiler creates a second function for each type used, generates only functions that appear for types that appear in the code. But, computers are good at that stuff. It's pattern matching, basically. Now, you can do really powerful things with this, right? Because pattern matching is a powerful concept. Also, you can overload them. You'll see that you can do some real trickery with templates. Our goal, so yeah, that was function templates. Now we're going to make a class template. We're going to see it's quite easy, right? Because again, we're not changing any logic. We're just changing the types. We're inserting generics. And then when we run it, well, then there's a couple things you have to watch out for, but for the most part, everything just works, right? Templates aren't that difficult, at least at the level that we're using them. So class templates, well, basically, again, in our class, we want to have a generic type. It can be used anywhere that we use a regular type, right? We can have it as a data member. We can have it as a local variable in a function or a parameter to a function. And this is often used for collection classes because collection classes, we don't care about the type. We just want to be able to add and remove things and yada, yada, yada. On your assignment, I ask you to take a array back to list and change it into a template. And so we're going to do something similar here, but we're going to do it for a linked list, right? Just so that it's not exactly the same. But you'll see that it's very easy. So, well, this list is for a list of books. And specifically, it's a list of book pointers. So we declare a bunch of books here. And then we add the address of each of those books to our list of books. And then we print them out. So we're going to do that. And then we'll change this to a templated version of this. And then use it with other types. All right, so there's our list of books. So everything works great. So let's change it to a template, which is not going to change anything except for this declaration. We want it to be a list of book pointers. Everything else should work exactly the same. Okay, so here above list, we're going to use the template declaration. Oops, class T. Now our list is no longer a class, it's a template, okay, which implies certain things. We're going to get rid of this for now because it's just trouble at this point. We'll come back to it and the implementation as well. So we're going to start out simply. And simply speaking, so right now it stores book pointers. We want it to store this generic type T, so we're going to replace every instance of book pointer with T. Basically, we're going to do what the compiler does later, but in reverse, right? So this gets replaced with, actually we have 3 of them here. Replace them all with T. Now I could just do a find replace, right? But I'm going to inspect it just to make sure there's nothing, no hidden details that I'm concerned about. This will go as T as well. Okay, so that is the declaration. And below that, I have the implementation, right? So this is when you make a templated class, the easiest thing to do is to make it a header-only class, right? So we do not want to separate these into header and source or implementation. We're going to keep them all in the same file, and we'll explain why, or try to explain why later. T, why not T? I'm not sure T where. I'm not sure exactly which part you're referring to. Maybe that was earlier. Maybe I missed that question. Okay. So now these are the implementations, right? Usually these would go in our .cc file, but we're just going to put them here. And each of these now is also a template. So we're going to put a template declaration. And also, there's no such thing as a list anymore. There's only a list of type T. But otherwise, this looks good. This implementation is fine. Oh, T star. Ah, good question. Well, let's think about what other things I'd want to store in my list. So now I'm saying, whatever I store, I'm not going to actually store that thing. I'm going to store a pointer of that thing. Right? So I'm sort of restricting now what you're allowed to store. And in particular, if we go here, now this is going to store a list of pointers to integers, which is I mean, maybe not what I want, right? I just want to make a list of ints. So I just put t, I can, instead of t pointer, because, I can decide to store book pointers or books themselves, right? So I want to have that flexibility, essentially. Yeah, the list stored book pointers, but this declaration here ensures that t gets replaced with book pointer. So I'm still storing the exact same thing. But by not storing it as a t pointer, that means I can also store a list of ints, right? So that's, again, we're trying to write it as generally as possible. Yes, exactly. If I declared it this way as list book star, then it would actually be storing double pointers. So I would have to change this declaration to store just a book. And then behind the scenes, it would store book pointers. But now I got to do, well, it's a little more restrictive. And I can choose to store pointers or I can choose not to store pointers. That's kind of my goal, right? So yeah, we're going to replace all instances of book pointer with t. Down here, we're going to declare this a template. And of course, there's no such thing as a list. There's a list of type t. I'm going to replace all instances of book pointer, which there are none. All that logic is fine. Template t, that's okay. Template t, this is of type list t, and book pointer gets changed to t. That's the only place it is. Oops, t, book pointer. All right, so this is, I'm also going to change book to little t. And so now this becomes little t. And that's good. Incidentally, book. So this is going to be t little t equals whatever data I decided to store and then return little t. So it's a good idea to go through this at least once, eh? But this is like, really, this is the type of things large language models were made for. If you have a big class, you don't want to do all this by hand. Large language models really are just pattern matchers. And so they would, I would guess it would be almost perfect every time if you did it this way. Not that I'm suggesting anything. Okay, so it looks like we have a functioning list template. None of the logic has changed, but I just replaced all instances of book pointer with t. And so now this should still work exactly the same. So let's, well, of course, it never worked exactly the same. 89. Did I forget the template declaration? Yes. All right. P3, there we go. It works exactly the same, which is what I wanted. But now, so the compiler just did the opposite of what we just did, right? So the compiler looked here and said, oh, you want a list of book pointers? Well, I do have something in this file that matches that, right? I have a template for a list class. And then it just copies and pastes that list class along with all the implementations. It does a find replace each instance of t and replaces it with book pointer. And of course it works because we did just the inverse of that just a moment ago when it was working. And so yeah, we get back basically a class that will store book pointers. But of course, in addition to that, we can make, well, this didn't, this compiled, right? I forgot to take it out. And so, well, let's try and use it. We should be able to add ints to it and then print out ints. Now, going to do this. I called it list ints. List ints, now these are not pointers, so I'm not going to dereference them. And yeah, so I can store book pointers or I can store ints, both work. Now, 2 new classes were generated based off that template. But everything works fine. So questions? Yeah, so that's what you're expected to do for the tutorial. Again, it's not that difficult. There are a couple gotchas that I'll show you, right? They're not really huge gotchas, but let's say that we wanted to do something like this. Instead of explicitly, using a for loop to print out all my ints, I just want to overload this operator for this list class. Now this list class is a template, so it's not quite that simple. And then in here, let's say cout list books end line. Okay, so we made a list of books, a list of ints. We want to overload this stream insertion operator. So let's do that. Now, here is the friend declaration. Now, this is in some sense also like just a declaration. It's the same as any old declaration that I might put outside of a class, right? So I'm just declaring that there exists this function. Here's the function signature. Well, this is not actually a function. It's a function template. So I do have to use the template declaration. There is a problem, though, if I do this, right? These are variables. Like t is, in some sense, a variable, and they have scope. And the scope of this t is the list class, right? I can, use t here and here and here. And what I'm doing here is I'm, in some sense, declaring another variable of the same name, right? So in terms of when we do that with variables, what happens is we end up shadowing the previous variable, and then we can't access it. And if we try to do that, the compiler will actually not let us do it. Well, it does a bunch of stuff. But one of them, if you scroll up to the top, the first error you'll see is that this parameter shadows the previous parameter. So I'm not allowed to do this. If I declare a template, like a friend function template, then I have to use a different variable from this one. Also, there's no such thing as a list. I have to define it as a list of type V. So that's our declaration. Our implementation will go down. Actually, let's see if that compiles. Yeah, it does a lot of type conversions. Okay. All right. Well, let's do this then. Template. I can use T here, right? I used V above. I used T here. That's all fine. This is now a list of type T, and so is this. Okay. Let's try to compile that. All right. So I get a weird error now, saying current node was not declared in this scope, but I did declare it, right? This is the declaration right here. But the compiler is confused. I can't, in terms of like generating this where I can show you like why this would be ambiguous. I have not been able to do that, but this is to the compiler ambiguous. I think because it's a templated type, which means that, I don't know. It means we don't necessarily know what node is for some reason. So what the compiler is thinking is that, well, I might be, this might be a variable, and I'm multiplying it times this thing. But the compiler does not know for sure what you're trying to do here. So we have to give it a hint. So I'm going to use type name here, and that tells the compiler that, no, this is not some, generic variable. This is actually a type. And that means this is a pointer declaration, and this is a variable. Okay. Now, Again, the very specifics of why that happened, I cannot seem to reproduce it or figure out what is ambiguous about it, but it is, apparently. According to this compiler, there is some ambiguity here, which we have to resolve using this type name declaration. All right, so again, that's not a lot of information, but just if you ever bump into that problem, this is how you solve it. Good questions? Okay. Now we should have something that works. Hey, look at that, everything compiles. All right, so we have a list of ints and we have a list of books. What did we print out here? What is this? Yeah, these are memory addresses. Technically, I printed out, it's a list of book pointers, and I printed out the pointers, right? So the solution, I could try to dereference that. Of course, if I do that, oh, well, now it does not compile for ints, right? This would actually compile if I commented this out, right? Because it only makes a class with the types that I declare. So it works if I comment out the ints, but now if I try to make a list of anything but pointers, then over here, this is going to fail, right? If I try to dereference anything other than a pointer, I get a compilation error. So you have to be careful now that we generalized our data types. That means I cannot be making too many assumptions about what people are storing there, unless I want to restrict what types people are allowed to store. But yeah, doing stuff like this is, well, it's a little bit tricky now. And in fact, for something like the vector class, they don't do this at all, right? So for a vector, what you can do is you can write this stream insertion operator for a vector with a specific type. And then, so if you're storing, if you know that you're going to store a vector of ints, then you can write this for ints, not a templated function, but a regular function. And then it'll work for ints, and if you tried it with a vector of anything else, it just won't work. So that's generally the solution, sorry. All right, questions? Okay. So yeah, that is to say, if you decide to do something like this on your assignment, be aware, right, of the types you are using, because if you use the wrong type and try an operation that doesn't work, it's not gonna compile. Okay, 928, and that's basically 90% of what you need to know about templates, right? Easy stuff. There's the one little gotcha of like, hey, they may choose to store pointers. And if they choose to store pointers and you make an assumption that they're not storing pointers or that they are, you could end up with a compilation error. Also, it's the same as the functions. These are actual classes that get built in sort of a pre-processing step, right? They copy and paste all those things and then they try to compile them. If they compile, well then great, you got a new class. And if they don't, well, you get a compilation error. And yeah, watch out for this. If I declare a templated function inside my class, then I should use a different type variable here. The difference between class and type name in template declarations is 0, as far as I can tell, right? To the best of my research, again, all 10 minutes of it, but still, I think I had some good sources. Type name does have some other uses, right? So we saw how the compiler can get confused about things that something that might be a variable or might be a type name. For whatever reason, the compiler cannot parse that. I'm not sure why. There is a good Stack Overflow post, but this PDF viewer does not allow hyperlinks. I'm not sure why. Yeah, so this is a new class for each type, yada, yada, yada. All right, and that's basically what you need to know for your assignment. We're going to go over a few more things, right, such as multiple types, non-type parameters. So I can, instead of passing in a class or a type, I can pass in an int, right? So we're going to see how we can do that. And then default types. You can think of the list of generic items or elements or whatever is just a parameter list. And as a parameter list, I can assign default types to those. Okay. So we have here an array of map items. Map item is a class that we made. So I'll show you it in a second. But basically, if you've used like a dictionary, then you have like a key value pair. So here I'm going to set, for the key 10, I'm going to set the name to Bobby, and for the key 22, I'm going to set the name for Mike. These are old-timey hockey players. Some of these are even before my time. The map item class, we're going to change it to a template, but for now, it really just has a key as an int and a string as the value, and I set some int to be the string. And yeah, so I just take individual array locations, and I can set those locations to be a key value pair, and then I can print those things out. So let's make our map of hockey players. All right, well, maybe it'll work. Permissions none. All right. Jeez. Okay, so there's our map of hockey players. So all we're going to do is we're going to change this to be a template because we might want to make down here we want to reuse this sort of map type, but here we want to store students and their grades, right? So Timmy has an 11.9 GPA, Harold has a 6.3 GPA, etc. Well, we saw this before, actually. Class K, class V. Right, so we can declare two different types. Now, of course, every time we refer to a map item, we need those two types. So, for instance, here, in this function declaration, there's no such thing as a map item. There's a map item on two types, in this case, S and T. Set, this is going to be set our key to this value, and this will be a K and a V. Now, the implementation, of course, I also have to do. Oh, I did not explain why. I'll get to that in a moment after this example. I did not explain why we keep everything in a header file instead of separating them. So yeah, this should work. This is now a template function with types K and V. And yeah, we are going to make the assumption that keys, Ks and Vs, whatever they are, can be sent to the output stream. All right, so this should work still with our hockey players, but of course we have to now define what's int and string. And down here we define it as string and float, and both of these should work. So there we go. Now our map item can be used with any type, basically any type that can be printed out to the output stream. All right, questions? Okay, so as promised, again, we put the map, the declaration for the class and the implementation into the same file. So why do we do that? Or why is that recommended? I mean, there are ways around it, actually, and on your final, we do some of these things, and you'll see it on your practice final as well. But the reason is, of course, if I don't have a type, if I don't declare this, right, So there's no class map item until I make a declaration that looks like this. And then I say, oh, please try to make a class of type map item on ints and strings, and the compiler goes ahead and does that. If I don't have any declaration, then the compiler can't compile it because it doesn't know what types to use, right? And so if I separate it into list.h or mapitem.h and mapitem.cc or list.h and list.cc, and I try to compile list.cc, well, what's it going to compile into? I haven't given it any types, right? So the easiest solution is just for templated classes to keep everything in the header. And that way, right, so we include, in this case, map item. And then if we don't use map item, then nothing gets built. If we make this declaration, then it goes off and it builds a map item class based on those two types. And then down here, it does the same thing. And it has all the information it needs to make the entire class, right? Both the declarations and the implementations. So yeah. There are ways you can, if you know beforehand what types you need, you can split it into a header and a .cc file, and then at the top of the .cc file, you can kind of list like all the things you want the compiler to build, right? So you say, I'm going to need a list of book pointers, I'm going to need a list of integers, and I'm going to need a list of students, right? And then the compiler will build those three classes for you. So there are ways around this, but you have to know beforehand what types you need. All right, questions? Okay, let's, I'm going to try and get this through this part quickly. Now, these are so close together in name that I mess this up all the time. So sort of bear with me here. But basically what we're going to make, or what we already made, we're going to finish making it, is a light wrapper around that raw array of map items. So this is called mymap, and what we want is an array of map items. And mymap is, of course, parameterized in terms of it's a template. And so I want to declare something like this. So inside my mymap class, I'm going to declare an array of map items. Now, most of the times when I declare a map item type, I have to give it specific types, right? So here I'm giving mymap int and string, but inside another templated type, I can just use whatever generic types there are, right? Again, just imagine I'm the compiler, I copy and paste this, I do a find replace, T with int and V with string. Well, if I do that, then this will then go from here, it'll jump to the map item template and try to build a map item type, right? So you can kind of nest, you can nest these templated types together, essentially. Yeah. All right, so yeah, I need a, let me cheat. Well, let me do this. Size equals 0. I'm going to write the add outside here just for fun. Void add. Oops. Okay, so now similar to our other, sort of array implementations, I want to add this next key value pair to the back of the array. But I want to do a bounds check first. So I'm going to say if size is greater than or equal to max size. Let's throw. All right. So we haven't gotten to exceptions yet. I'm going to start using them. So that you'll learn a little bit about them before we talk about them. The first thing you might notice is that I'm just throwing a string, right? And in fact, not even a string, but a string literal, like a const character pointer. Which you're allowed to do. In C++, you can throw whatever you like, right? You can throw an int, you can throw a type you made yourself. You can also throw an exception. But here we're just going to do this because, well, we're not actually trying to catch anything, so it's just going to crash, which is good. That's what we want. If we're out of bounds, we just want to crash. We can catch that and handle it later if need be. All right, otherwise, items at size plus plus. Now that's going to return a map item, and I'm going to set the key value pair. Right, so I look at the next empty location at size, and then I increment size after using the postfix operator. And then I set that to the key value pair. And when you run out of space, it just throws this error. All right. This is items. And I think everything else is good. Okay, so yeah. What we're trying to show here is a templated type inside of a templated type. Of course, it never quite works the way you want it to. K was not declared. Everything. T, oh, what am I doing? M has no member items, is that right? Sure looks like it does. Friend. All right, well, here's a good exercise. Anybody spot what's, oh, maybe it's up here. Max size. Capacity, sorry. All right, so yeah, these are fixed size arrays of size capacity. Yeah, as usual, right? So if you're looking at the lowest error, that's not usually accurate. The first error is usually the one that spawns the rest of the errors, right? So always scroll to the top when trying to debug and check that first. Unresolved overloaded function type. This, you know, this just never goes smoothly. Size, oh, no, that's good. I don't know. Anybody spot the error? Yeah. The which one? Oh, yeah, you're right. You're right. I have to scope this in. Excellent. Good call. Like that, right. Yes, so it could not resolve it because I did not scope it in and tell it that this was part of the class. All right, so there's our map item, our key value pairs, or our my map. Somebody in the chat get it? Yeah, okay. So now if we try to add a fifth hockey player, right? We're going to add Sue to our old-timey hockey team. It compiles just fine. Terminate called after throwing an instance of, you know, a const character pointer, basically. So that's what I threw, and it just crashed. It did not print out my string, but whatever. It crashed. That's good. We don't want it to sort of silently corrupt memory. So while this also poses a problem, right? If I make a class and I have a statically allocated array inside that class, it has to be a fixed size, right? The compiler needs to know beforehand what the size of each class is. But when I make a map, a my map, sometimes I want to store 4 things, sometimes I want to store 8 things, right? So I want to be able to define what this capacity is. So I'm going to do that by adding a third type here. The type is an int now. So this is a type of class. So v is some type, like a class or an int or whatever. But an int is, of course, going to be a value, like 4, 5, 6. And I can do that. It does change all these other declarations. And it does change my map from when I declare it from being 3 parameter or 2 parameters to 3. Right, so down here, this is also going to be capacity. All right. This int c, right? Even though I don't use it, oh no, I do use it here. Let's call this capacity. Right, so this capacity is the same as this capacity now. Here I'm just going to use int c. And here I don't use it, but it's still part of the declaration, so I do need it. Now when I declare my hockey team, I can say, well, I need enough room for 5 players. Right, and then, well, of course it doesn't work. What did I do? Oh yes, I have a couple. Here, this should say capacity. I think that's it. Nope. Let's add. Oh my goodness, now what did I do? Never goes, this one never goes smoothly. I don't know. I can't, number of template arguments. 3 should be 2. Oh, my map item, yes. So map item was still only 2 template arguments. Right, good. If you actually read the compiler thing, sometimes it tells you exactly what the problem is. All right, so now I can make one that stores 5. Now it's important, right? Somebody did ask, well, why can't I just pass in the capacity as a constructor argument? So why can't I do that? And I guess the answer is you can, but then you have to change a few other things. The reason why we can't in this case is that this is a statically allocated array, and we need to know it has to be a hard-coded size. Right? So I cannot, at runtime, decide what size this is, because all of my map classes have to be the same size. But of course, when we call, for instance, if I made a mymap2 or something like that, oops, and I used 6 here, well, these are not the same class. So they're allowed to have different sized arrays, statically allocated arrays. Right, so that is sort of the, now that's a lot of overhead, right, just to try to pick the size of an array. So, you know, maybe a better idea than this would be to put an array on the heap, and then I can decide at runtime what size I want it to be, and then I could pass in the size in the constructor. That might make more sense. Of course, this, if I absolutely must have a statically allocated array inside my class, then this would probably be the better pattern. All right, questions? Okay. And as a final thing, well, maybe I don't always want to define the capacity, right? That's kind of a pain. So I can just say by default, give it a size 4. That means when I look here, I can just not pass in that final parameter. And, well, then I have to not add Sue. It compiles, it runs, and then I can, well, I can say make it of size 5, and then let's add Sue. And there we go. So, right, so I can use default values, and not just here. I can also, well, you can think of this as a parameter list, right? And so like any parameter list in C++, I can use default values, but all the default values have to be to the far right, right? So if I want 2 default values, they have to be the last 2 things in my list. So I can do something like this. I can say, well, I want you to define the key, but the value is most often going to be string, so I don't really need you to do that. I can just declare a MyMap of type int. That tells the compiler that I want to build a MyMap of an int and a string and a size 4. Right, so that still works. And then I can say, well, let's give it a default value of int for the first one. And now I can declare a MyMap with no parameters, and it should still work. Well, you know. What did I do? I did not save. Right, so it still works. I have all default values, and then I can define, right? But the order is important. That's the only catch. It always has to be to the far right. Any non-default values are all to the left. So yeah, questions? All right, well, that might be a good place to stop. Yeah, so something to keep in mind, right? That is, I can pass in an int and make 2 different classes with different size backing arrays, but that's like, those are separate classes. So static variables, for instance, will be different for those 2 classes. And maybe that's not really what I want. Maybe I want to put that backing array on the heap. And if I make a map of an int string pair, then maybe I want all of those classes to be the same regardless of the size of the backing array, right? So those are design decisions you have to make. We'll stop there for today. Yeah, Thursday we will start with WooClap and then move on to files and streams. So yeah, we'll cut it out. Logically, it's just a good place to stop. So we'll stop there for today. Also, everybody's leaving, so I'll see you guys on Thursday.